Hi everyone, and welcome to class number 20 of Physics 218 at Ithaca College. So yes, I am at home right now. So you're in my living room, and you can see the kitchen actually behind me there. So I recognize that this is a new and weird and difficult situation. I'll admit it's a little funny for me to be talking to a camera right now instead of to all of your faces, but we'll do the best we can under the circumstances. Okay, so last time, and I know this was a while ago, it certainly feels like an age to me, last time we were talking about how particles in quantum mechanics act like waves. We talked about interference experiments you can do with single atoms or molecules. And then we introduced this hypothesis due to Louis de Broglie that particles have a wavelength, the de Broglie wavelength, given by Planck's constant h divided by the magnitude of the momentum. Today, what we're going to try to answer is the following. We're going to talk about how we can describe quantum waves. As you see it in the reading, the answer is via the wave function. We're going to talk about what the wave function capital psi of x and t means. We're also going to, at the end, talk briefly about where the wave function comes from. Okay. So let's just have a little bit of a reminder of what we did last time. Okay. So when we talked about experiments last time, so we did interference with atoms and molecules. And in a few minutes I'm going to actually cut to a PhET simulation of this very type of experiment. I know not all of you necessarily have access to PhETs right now. We're trying to see what we can do about that. So I'm actually going to switch to screencasting from my computer so that you can at least see some of the things that I would like you to see in the simulation. Although if you do have access, you should definitely try playing around with it yourselves. So we'll look at a PhET of this. The other thing that you read about for today, and we'll also look at a simulation of this, is what's called the Davisson-Germer experiment. And namely, this is an experiment where we do diffraction of electrons from planes of atoms in a crystal. So actually, let's now go to the PhET and let's see what it shows us about these two types of experiments. Okay, so this is the quantum wave interference PhET simulation. So what we've got here is we have this sort of stylized particle gun. I've got it set to shoot neutrons here at a double slit. We've got a screen back here. So let's see what happens when I turn the gun on. And now this is high intensity, so it's spraying out. You can think of it as a continuous beam of particles. Several ways to look at this. we can look at the average intensity, which is what I'm seeing now, and you can clearly see, right, that there's a central maximum and then these two secondary maxima, just like you would expect for light. Now, a few things to know. What you're seeing in this simulation in here is you're seeing the wave function, which is, as we'll talk about how we'll describe quantum waves, you can switch from viewing, right now we're seeing the magnitude, where you can also look at just the real part, or just the imaginary part of the wave function. And we'll have more to say about what that all means in the next couple of classes. Some interesting things that are worth noting. So right now I've got this displaying average intensity, but I can also show discrete hits on the screen. And it'll be easier to see if I sort of turn down the gun a little bit. When we go to discrete hits, what you can see is that even though the neutrons have a wave-like nature, you still build up discrete hits on this detector screen that we're seeing. Now, let me pause this and let me switch it to a single particle view. Sort of things get even more dramatic if we shoot single neutrons. So if I fire a particle, and again, in a few classes, we'll talk about what this means mathematically. You saw there that even though the particle propagated as a wave, we got a discrete hit on our screen. Let's just watch that again. And now we got another hit, right? We can maybe now watch like the real part of the wave function. Here we got a hit somewhere else. I think you can see, right, that there's a probability associated with this. I can't predict exactly where on the screen the particles are going to hit. Just to see what it looks like, I'll set this on repeat, so it's just shooting particles continuously. And we're watching those quantum waves reach our screen, and we're seeing that interference pattern build up one hit at a time. So there's a lot of things you can play with, and if you do have access to the FET, I'd encourage you to think about playing with things like the width and separation of the slits and see what effects those have. I'm going to now pause and go back to the high intensity view for a second, and I'm going to ask you to make a prediction. So going back to average intensity, so you can see the pattern build up, and I'll turn up the screen brightness so you can see clearly. Notice that I have the velocity of the particles sort of in the middle right now. I'd like you to make a prediction. Namely, I want you to think about how this interference pattern would change if I slowed the particles down. So if I were to drag the slider from where it is over to 0.4 kilometers per second, how would this interference pattern change? This will be a nice way to review what we were talking about last time. Okay, welcome back. Now that you've had a chance to think about what will happen when we slow the particles down, let's do it and see what happens. So I'm going to drag this over, and the pattern evolves, and I'll turn up the screen brightness just a little bit so you can see. I think you can see that the interference pattern has gotten wider. Now, why would this be, right? When we slow the particles down, right, we decrease the magnitude of their momentum. According to the definition of the de Broglie wavelength, when we decrease the momentum of a particle, we end up increasing the de Broglie wavelength since it goes like 1 over p. Then when we have particles with a longer wavelength and we think about diffraction. Remember how we talked about how like sine theta goes like m lambda over the distance between the slits, right? So when we increase the wavelength, we're going to increase the angles to the fringes, and that's why we get a wider looking pattern. Okay, so hopefully that's a reminder of what we did the previous class. I just want to take a minute now to show you also the Davisson-Germer experiment. So it's the same sort of idea here. So we have a simulated particle gun that's shooting electrons now. These red dots represent atoms in a crystal. So in a crystal, the atoms are arranged in a periodic regular lattice. And you can see that the atoms form these lattice planes here. And if we turn this electron gun on, I can shoot one at a time, I think. But let's just turn it up. Let me go hit play. There we go. If we're now shooting electrons, right, you can see what's coming back, right? If we look at the wave here, right, you can see that there are some angles, if I like, where there's a lot more wave coming back, and other angles where there's less wave coming back. It might be clearer if we look at a plot of this. So if we look at an intensity plot here and watch that and watch that build up, again, you can see where there are angles with more intensity and less intensity. The point here again being that these electrons really do act like waves. This is exactly what you would expect to see if you were shooting X-rays at a crystal. And again, this is a nice simulation to play around with if you're interested.